Hello there, and welcome. Tonight I want to take you somewhere beyond the ordinary boundaries of our everyday existence, to a place where light itself surrenders to forces so profound and mysterious that even our greatest scientific minds find themselves contemplating questions that seem to touch the very edges of what we can understand about reality itself. I want to invite you to journey with me into the realm of black holes, and more specifically to explore one of the most fascinating and perplexing cosmic phenomena that has ever captured the human imagination. The event horizon, that invisible line in space where light itself becomes trapped, unable to escape, marking the point of no return into the ultimate cosmic mystery. As you settle in, perhaps in the quiet comfort of your own space, away from the noise and demands of the day, I want you to know that you're not alone in this exploration. You and I were going to think about something together tonight that has puzzled astronomers, physicists, and philosophers for generations. We're going to contemplate the profound implications of a place where the laws of physics behave in ways that seem almost impossible to our everyday intuition. But before we journey deeper into this cosmic darkness, I want to ask something of you if you found yourself drawn to these kinds of cosmic mysteries, these questions about the nature of reality that keep us awake at night. If you love exploring the wonder and strangeness of our universe, would you consider liking this video and subscribing to join us on more journeys like this one? Your support helps bring these contemplative cosmic stories to more people who share this sense of wonder about the stars above us. And I'm genuinely curious, where are you watching from tonight? What time is it where you are? Please take a moment and tell us in the comments below. Are you watching from a quiet room in the evening, or perhaps from somewhere else entirely? What's drawing you to think about black holes and event horizons on this particular night? I'd love to know where in this vast world you're experiencing this moment with us. Now, it's a question that at first glance might seem impossible, even absurd. How can light, the fastest thing we know in the entire universe, the very thing that defines the upper limit of speed itself, ever be trapped? How can anything escape so slowly that not even light can outrun it? Light travels at 300,000 kilometers per second, and yet we're about to explore a place where even this incomprehensibly fast phenomenon becomes a prisoner, unable to break free no matter how hard it tries. It's a concept that challenges our basic understanding of how the universe works, and yet the evidence is there, waiting quietly in the cosmic darkness for us to unravel its secrets. What if, just maybe, this point of no return isn't a barrier at all, but rather a revelation about the very nature of space and time itself? What if the event horizon is teaching us something fundamental about how our universe is actually constructed at its deepest levels? As we begin to contemplate this mystery together, I want you to imagine yourself standing on a cosmic shore, looking out into an ocean of space so vast that human understanding seems almost impossibly small. You're looking at something that exists only in the most extreme environments the universe has to offer, places where gravity has become so intense, so overwhelming, that it has fundamentally warped the fabric of reality itself. The event horizon is like an invisible boundary drawn in the cosmic ocean, and beyond that boundary, the rules of the game change completely. It's not that light is weak or slow there, it's that space and time themselves have been twisted so profoundly that escape becomes physically impossible, not because of any barrier you could see or touch, but because the very direction that would lead away from the black hole has been bent back toward it. Picture this with me for a moment. Imagine a powerful whirlpool in the ocean, one so perfectly designed, so precisely calibrated by the forces of nature, that once you cross a certain invisible line, the current pulls you inward no matter how fast you swim. Now imagine that this whirlpool is so extreme that even light, the fastest swimmer imaginable, cannot escape once it crosses that threshold. This is, in essence, what we're talking about when we speak of the event horizon. It's a boundary beyond which escape velocity exceeds the speed of light, which according to everything we know about physics means escape becomes impossible. But here's where it gets truly fascinating. This isn't just some theoretical idea that scientists dreamed up in their offices. This is something we can observe in the universe, something that has real consequences, something that affects the actual cosmos around us right now, at this very moment as you're reading these words. Scientists and astronomers have been studying black holes and event horizons for decades, and the story of how we came to understand them is itself a journey through human curiosity and wonder. It begins, in many ways, with Albert Einstein's revolutionary theory of general relativity, which fundamentally changed how we think about gravity. Einstein showed us that gravity isn't actually a force pulling things together in the traditional sense that Newton described. Instead, gravity is the curvature of space and time itself. Massive objects like stars and planets actually bend the fabric of space-time around them, and what we experience as gravity is really just objects moving along the curved paths created by this bending. It's a profoundly beautiful idea, and it opened the door to understanding how something as extreme as a black hole could actually exist. Now, in the decades following Einstein's work, physicists began to explore the mathematical implications of his equations, and they discovered something remarkable. If you took Einstein's equations and applied them to objects of extreme density, objects where an enormous amount of mass was compressed into an incredibly small space, the mathematics pointed to something unexpected. There would be a region of space-time so warped, so intensely curved, that it would create this invisible boundary, the event horizon. And beyond that boundary, time and space would behave in ways that seemed to violate our everyday experience. The equation suggested that once you crossed that line, you would inevitably be pulled toward the center of the black hole, and there would be nothing you could do to prevent it. No amount of speed or force or willpower could overcome it. For a long time, many physicists weren't even sure if black holes were real. They seemed like mathematical curiosities, strange solutions to Einstein's equations that perhaps existed only in the realm of pure theory. After all, how could something like that actually form in nature? How could gravity become so overwhelming that it could trap light itself? But then, as astronomical observations became more sophisticated, as our technology improved and our telescopes reached further into space, astronomers began finding evidence that black holes weren't just theoretical, they were real. They existed in our actual universe. They were out there, in the darkness between the stars, silently bending space and time around themselves, creating these regions of no return that fundamentally challenge our understanding of physical reality. The discovery of these cosmic objects has been gradual and fascinating. In the 1960s and 1970s, astronomers began observing strange sources of X-rays in the sky. These X-rays were coming from regions in space that didn't seem to contain any visible matter, no stars, nothing that you could see with ordinary telescopes. But the energy being released was enormous, far too much to be explained by conventional astronomical objects. Some scientists proposed that these X-ray sources might be black holes, feeding on material from nearby companion stars, pulling in matter and heating it to incredible temperatures before it crossed the event horizon. The intense heat and friction would produce these powerful X-rays that we could detect from Earth. As observations accumulated, the evidence became more and more convincing. Black holes weren't just possible, they were real. And then, in recent years, we've been given an even more direct window into these cosmic mysteries. In 2019, something absolutely extraordinary happened. Scientists associated with the Event Horizon Telescope project released the first ever direct image of a black hole's event horizon. They had used a network of radio telescopes spread across the Earth, coordinating observations across an enormous baseline to achieve unprecedented resolution. What they captured was an image of the supermassive black hole at the center of the galaxy M87, and what they saw was that glowing ring of light surrounding the dark region of the event horizon. It was breathtaking. It was a moment of profound human achievement. We had finally seen, directly and unambiguously, the boundary between the universe we know and a realm that lies forever beyond our reach. But you might be wondering, as many people have when they first learn about these things, if light can't escape from beyond the event horizon, how did we see anything at all? How could we see that glowing ring if it's supposedly a boundary beyond which light can't emerge? This is where the subtlety and beauty of the phenomenon reveals itself. The light we saw wasn't coming from beyond the event horizon itself. It was coming from material that was being pulled toward the black hole. Material that was still outside the event horizon but moving toward it at incredible speeds. As this material accelerates, as it's heated by friction and gravitational forces, it emits tremendous amounts of light and radiation. And then, as it approaches the event horizon, some of that light is deflected by the intense gravity and finds its way back to us. We see the silhouette of the event horizon itself, outlined against the bright glow of material being consumed by the black hole. This image, this first direct visualization of the event horizon, represents more than just a cool photograph. It's a profound confirmation that our understanding of gravity, that our interpretation of Einstein's equations is correct. It means that the universe really does work in these strange and wonderful ways. It means that space and time really are interwoven into a fabric that can be bent and curved and twisted by massive objects. And it means that there really are places in the cosmos where the rules change, where light itself becomes helpless, where escape becomes impossible no matter what you do. It's almost incomprehensibly profound when you think about it, when you really let it sink in. Somewhere out there in the universe, right now, matter is being pulled across the event horizon of black holes, crossing that invisible line and entering a realm where we cannot follow, where our understanding breaks down, where even the very concept of escape ceases to have meaning. Now, if you've made it this far with me, if you're still here contemplating these cosmic mysteries, I want to know what you're finding interesting about this. What aspect of the event horizon captures your imagination? Is it the fact that light can be trapped? Is it the implications for our understanding of physics? Is it simply the wonder of knowing that such extreme places exist in our universe? Please leave a comment below and tell me what's resonating with you as we explore this mystery together. Your thoughts and questions help shape how we think about these profound cosmic phenomena, and I genuinely want to know what's drawing your attention as we journey deeper into this darkness. As we continue our exploration, I want to start moving us from the broad context of black holes toward a more detailed understanding of the event horizon itself. You see, the event horizon isn't just some random cosmic feature. It's intimately connected to the properties of the black hole it surrounds. The size of the event horizon, something we call the Schwarzschild radius, named after the physicist Carl Schwarzschild who first calculated it, depends entirely on the mass of the black hole. For a black hole with the mass of our Sun, the event horizon would be about 6 kilometers in diameter. But for a supermassive black hole, like the one at the center of our own galaxy, with millions or billions of times the mass of our Sun, the event horizon could be millions of kilometers across. Despite their difference in size, though, they all work on the same principle. They all create regions of space-time that are so warped that escape becomes impossible, and this brings us to one of the deepest questions we can ask. What exactly is happening to light when it approaches the event horizon? We often talk about the event horizon as a point of no return, and that's true, but what does that really mean? Light doesn't hit some invisible wall and bounce back. Light doesn't slow down gradually as it gets pulled into a black hole. Instead, something far more subtle and profound is occurring. As light gets closer and closer to the event horizon, the very fabric of space around the black hole is becoming more and more curved. From our perspective, watching from far away, we would see the light moving more and more slowly, its wavelength becoming more and more redshifted as it fights against the intense gravity. Eventually, we would see it move so slowly that it would effectively come to a stop at the event horizon itself. But this is only from our perspective, observing from a distance. For the light itself, if we could somehow ride along with it, something different would be happening. Time itself would be slowing down relative to distant observers, and the geometry of space would be changing dramatically. This is where general relativity reveals its truly mind-bending implications. Near a black hole, space and time don't behave the way we experience them in our everyday lives. Time moves differently depending on where you are relative to the black hole. Someone standing very close to the event horizon would experience time passing differently than someone far away. This isn't just a theoretical mathematical abstraction. It's a real physical effect that has been measured and verified through careful observations and experiments. And as you approach the event horizon, this effect becomes more and more pronounced. Time slows down more and more relative to distant observers. At the event horizon itself, from the perspective of a distant observer, time would effectively stop. This is deeply counterintuitive, almost impossible to wrap our minds around. But it's what the mathematics of general relativity tells us, and observations have confirmed it again and again. So when we ask why the event horizon is the point of no return for light, we're really asking a question about the geometry of space-time itself. We're asking how space and time are configured in this extreme environment. And the answer is that, at the event horizon, the curvature of space-time reaches a critical point where escape velocity becomes equal to the speed of light. You see, every object, no matter how massive, has an escape velocity, the speed you need to travel in order to escape its gravitational pull entirely. On Earth, escape velocity is about 11 kilometers per second. For our Sun, it's about 618 kilometers per second. For more and more massive objects, the escape velocity gets higher and higher, and in the mathematics of general relativity, there's a special relationship between the mass of an object and the radius at which escape velocity equals the speed of light. That special radius is the Schwarzschild radius, and the surface at that radius is the event horizon. What's absolutely fascinating is that this isn't a barrier made of anything material. There's no wall there, no force field, no physical obstacle. If you could somehow approach the event horizon and cross it, you wouldn't feel any sudden change. You wouldn't hit something hard and get bounced back. Instead, you would gradually enter a region of space-time where the properties of space itself have fundamentally changed. The direction that leads away from the black hole would gradually bend back toward it. The further you went, the more extreme this bending would become, until finally, beyond the event horizon, there would be literally no direction you could move that would take you away from the center of the black hole. Every possible direction would lead inward, toward the singularity at the heart of the black hole. And then there's the question of what light actually does as it approaches this boundary. Light always travels in straight lines through space-time. This is one of the fundamental principles of relativity. But near a black hole, space-time itself is so curved that even straight lines through space-time become curved when we look at them in terms of ordinary three-dimensional space. So light, following straight paths through space-time, would appear to us to be curving more and more sharply as it got closer to the event horizon. At the event horizon itself, a photon, a particle of light, would be following a path through space-time that curves back on itself. It would be trapped in a circular orbit, eternally circling the event horizon, unable to move inward because it's trying to escape, and unable to move outward because the geometry of space-time doesn't allow it. This is often called the photon sphere, and while it's not quite the event horizon itself, it represents a critical boundary beyond which even light cannot escape to infinity. Think about this for just a moment. Imagine a beam of light, the fastest thing in the entire universe, and imagine it trying to escape from a black hole. The light follows the straightest possible path through space-time that it can take. And yet, because space-time is curved, because the black hole has warped the very fabric of reality around itself, that light finds itself trapped, unable to escape, unable to reach the distant stars that it could easily reach in any normal part of the universe. It's a profound humbling of even light itself, a demonstration of just how powerful gravity becomes when mass is compressed to extreme densities. And this is where our first 3 chapters of exploration will naturally continue forward, building upon these foundations of understanding and moving us deeper into the specific mechanisms and evidence that has revealed these cosmic truths to us. This profound inability of light to escape from within the event horizon isn't just a curiosity or an abstract mathematical prediction. It has real, measurable consequences that astronomers and physicists have been observing and studying for decades now. It tells us something fundamental about how the universe is constructed, about the relationship between matter, energy, space, and time. And as we move deeper into our exploration tonight, I want to take you through the detailed mechanisms of how and why this happens, the evidence that confirms it, and the deeper implications it holds for our understanding of reality itself. Let's begin by considering what we mean when we talk about escape velocity in more concrete terms. You've probably heard the phrase before, or at least encountered the concept. On Earth, if you throw a ball upward with a certain speed, it falls back down. If you throw it faster, it goes higher before falling back. But if you throw it fast enough, at that magic speed we call escape velocity, it will keep going up forever, never falling back to Earth. That speed is 11 kilometers per second. For Jupiter, with its enormous mass, escape velocity is much higher, about 60 kilometers per second. The more massive the object, the faster you have to throw something to make it escape. Now here's where it gets interesting. In the mathematics of gravity, as you compress more and more mass into smaller and smaller spaces, the escape velocity at the surface of that object gets higher and higher, and theoretically, if you could compress enough mass into a small enough space, the escape velocity would exceed the speed of light. At that point, nothing could escape, not even light itself. And that's exactly what a black hole is, a region of space where mass has been compressed so much that the escape velocity has exceeded the speed of light. But light is special. It always travels at the speed of light, nothing more, nothing less. It can't go slower. It can't speed up. The speed of light is a fundamental constant of nature, the ultimate cosmic speed limit. So if the escape velocity exceeds the speed of light, then light cannot escape. It doesn't matter how fast light travels, because the escape velocity is faster. Light will be pulled back, trapped, unable to flee the gravitational grip of the black hole. This is the fundamental reason why the event horizon exists, why it's the point of no return. It's not because of some mysterious force or some exotic physics that we don't understand. It's simply the consequence of gravity, mass, and the speed of light interacting according to the laws of physics that we've come to understand through Einstein's theory of general relativity. Now, you might be wondering at this point about the specific mechanisms of how this works in practice. How exactly does a black hole form in the first place? How does matter get compressed to such extreme densities that it creates an event horizon? The answer involves stellar death, the dramatic final moments in the life of massive stars. When a star much more massive than our Sun, let's say 20 or 30 times more massive, comes to the end of its life, it doesn't go quietly. Instead, it undergoes a catastrophic collapse. For most of its life, a star maintains a delicate balance. The force of gravity trying to crush all the star's material toward the center is balanced by the pressure from nuclear fusion happening in the star's core. Heat and radiation from fusion push outward, holding up the enormous weight of the star's material, but eventually the fuel runs out. When a massive star exhausts its nuclear fuel, this balance breaks down catastrophically. There's no longer enough outward pressure to support the star against its own gravity. The star collapses inward at incredible speeds. What happens next depends on how much mass the star has. If it's massive enough, and astronomers believe that roughly 20 to 30 solar masses is sufficient, the collapse doesn't stop at any intermediate stage. The material doesn't settle into a stable configuration like a neutron star does for less massive stars. Instead, it keeps collapsing, crushing down under its own gravity until it forms a singularity, a point of infinite density where all the star's material has been compressed. And surrounding that singularity is the event horizon, the boundary beyond which nothing can escape. The creation of this event horizon happens as the star collapses, as more and more mass gets packed into smaller and smaller spaces, as the escape velocity climbs higher and higher. Once the escape velocity exceeds the speed of light, once the density becomes high enough that the curvature of spacetime reaches that critical point, the event horizon snaps into existence around the collapsing material. From that moment on, the black hole is born, a region of space forever hidden from the rest of the universe. Now, throughout this cosmic drama, light plays a crucial role in what we observe. In the final moments before a star collapses into a black hole, it releases enormous amounts of energy. The core temperature reaches billions of degrees, nuclear reactions accelerate wildly, and the star explodes outward in what we call a supernova explosion. This explosion releases as much energy in a few seconds as our Sun will release in its entire 10 billion year lifetime. The light from these explosions can shine as brightly as an entire galaxy containing billions of stars. But here's what's remarkable. This spectacular light show happens before the black hole fully forms. Once the event horizon closes around the collapsing material, cutting off the black hole from the rest of the universe, no light from inside can escape anymore. The black hole becomes invisible, hidden behind its own event horizon, a cosmic secret locked away from our view. But that doesn't mean black holes are completely dark and invisible from a distance. This is where we encounter one of the most fascinating aspects of black holes, the material that gets pulled toward them. In many cases, black holes aren't isolated in space. They exist in binary systems with a companion star nearby. The black hole's gravity pulls material away from its companion star, drawing gas and dust into a swirling accretion disk around it. As this material spirals inward, as it gets pulled toward the event horizon, it accelerates to incredible speeds. Friction heats the material to millions of degrees, and this superheated material emits intense radiation, X-rays, ultraviolet light, and visible light. This is how we detect black holes, despite the fact that the black holes themselves are invisible. We detect the light from the material being consumed by them. We see the radiation from matter that's crossing the point of no return, and from this radiation, we can infer the presence of the black hole itself. If you're still with me at this point, If you're finding this exploration of black holes and event horizons captivating, I'd love to know what particular aspects are resonating most deeply with you. Is it the dramatic story of stellar collapse? Is it the profound implications of light being unable to escape? Is it the way we can observe these invisible objects through the radiation of doomed material being pulled into them? Please, take a moment and comment below. Tell me what's capturing your imagination as we journey through this cosmic mystery. Your engagement helps us understand what aspects of the universe are most meaningful to you, and it helps shape our conversation as we go deeper into these profound questions. The study of black holes and their event horizons has revealed something truly remarkable about the nature of spacetime. It's shown us that space and time are not fixed, unchanging backdrops against which physics happens. Instead, space and time are dynamic, flexible, responsive to the presence of mass and energy. They can be stretched and compressed, curved and twisted, bent and warped, and near a black hole this bending of space-time reaches its most extreme. The curvature becomes so intense that it fundamentally alters how objects move, how light behaves, how time itself progresses. This is one of the most revolutionary insights of modern physics, and understanding it requires us to think about space and time in ways that our everyday experience hasn't prepared us for. Let me try to paint a picture of what this means. Imagine space-time not as an empty, invisible stage on which the universe's drama unfolds, but rather as a flexible fabric, like a vast rubber sheet stretched out across the cosmos. Now imagine that matter and energy are like weights placed on this sheet. A planet creates a small dip in the fabric, the sun creates a much deeper indentation, and a black hole creates such a profound distortion that the fabric is pulled inward in a catastrophic way, creating a sort of dimensional whirlpool. Objects don't feel gravity as a force pulling them toward massive objects, at least not in the fundamental sense. Instead, they're simply moving along the curved paths created by the distortion of spacetime itself. They're following the straightest possible routes through a curved landscape, and the landscape is curved because of the presence of massive objects. When we think about light near a black hole, we need to remember that light is always following the straightest possible path through spacetime, something physicists call a geodesic. But near a black hole, spacetime is so warped that these straightest possible paths curve dramatically. Far from a black hole, in the relatively flat spacetime of the distant universe, light travels in paths that appear straight to us. But closer and closer to the black hole, the spacetime becomes more and more curved, and the paths that light follows must curve correspondingly. At the event horizon, the curvature reaches a critical point where the only geodesic available to light is one that curves back toward the singularity. There is literally no path through spacetime, no matter how light tries to move, that would take it away from the black hole and out toward distant space. Every possible direction, forward, backward, left, right, up, down, all lead inward. The topology of spacetime itself has changed completely. This is where the event horizon truly becomes the point of no return, not because of some exotic force we don't understand, but because of the fundamental geometry of spacetime in that region. It's a consequence of gravity, mass, and the structure of reality itself. And this realization brings us face to face with one of the deepest mysteries of physics. What exactly is happening at the singularity at the heart of the black hole? If matter is truly crushed to infinite density at a point, if all the black hole's mass is concentrated in a dimensionless singularity, then we've reached the limits of what our current theories can describe. The equations of general relativity break down. Time and space cease to have their usual meanings. We're at the edge of known physics, staring into the unknown. For decades, physicists have been grappling with this problem. What happens to matter once it crosses the event horizon? Where does it go? Does it continue to exist in some form that we can't perceive? Does it get destroyed? Does it somehow escape back into the universe through some process we don't yet understand? These aren't idle philosophical questions. They have profound implications for how we understand the universe. They touch on deep questions about the nature of information, the nature of reality itself, whether the universe is ultimately deterministic or probabilistic. The mystery of what happens beyond the event horizon remains one of the great unsolved puzzles of physics. And yet, even without fully understanding what happens inside black holes, we can say with confidence that the event horizon itself is real. that it functions exactly as general relativity predicts, and that it represents one of the most extreme and profound features of our universe. We've detected dozens of black holes now, each one confirming that the universe really does contain these incomprehensible objects, these regions where the rules change, where light itself is helpless. Each detection adds to our confidence that we're understanding the universe correctly, that our theories are capturing something real about how the cosmos actually works. One of the most exciting recent developments in our understanding of black holes came from observing the behavior of stars orbiting very close to the supermassive black hole at the center of our own galaxy. The Milky Way, our home galaxy, harbors a black hole with a mass of about 4 million times that of our Sun. This black hole, called Sagittarius A, is surrounded by a cluster of stars that orbit very close to it. By carefully tracking the positions of these stars over many years, astronomers have been able to map out their orbits with extraordinary precision, and these orbits follow exactly the predictions of general relativity. The stars move in elliptical paths around the black hole, just as planets orbit the Sun, but with orbital periods of only 15 to 20 years rather than the centuries or millennia required for planets to orbit our Sun. The precise shapes of these orbits, the exact speeds at which the stars move at different points in their orbits, all match what Einstein's equations predict. It's a beautiful confirmation that general relativity accurately describes the universe even in these extreme environments. Moreover, the observations of these stars have allowed astronomers to determine the mass and location of the central black hole with unprecedented precision. And when we use these measurements to calculate where the event horizon of this black hole should be, we find that it must be located at a radius of about 12 million kilometers from the center. It's an enormous event horizon by the standards of stellar black holes, but still quite small compared to the distances between stars in the galaxy. And remarkably, the stars' orbital measurements don't reveal any evidence that they're hitting any physical barrier, encountering any obstacle, or being affected by anything other than the gravitational field of the black hole itself. This tells us that the event horizon is exactly what theory predicts, not a physical obstacle, but a geometric property of spacetime itself, a boundary beyond which the very structure of spacetime has become so warped that escape becomes impossible. As we move deeper into our exploration, as we contemplate these cosmic mysteries more and more, it becomes clear that the event horizon represents something truly extraordinary about our universe. It's a place where light surrenders to gravity, where escape becomes impossible, where the rules of physics take on a character so alien to our everyday experience that it seems almost like science fiction. And yet it's real. It exists in our universe right now. Understanding why the event horizon is the point of no return for light requires us to truly grasp some of the deepest principles of modern physics. It requires us to abandon the notion that space and time are fixed, unchanging absolutes, and instead embrace the idea that they're flexible, dynamic, responsive to the presence of mass and energy. It requires us to understand that gravity isn't a force in the classical sense, but rather the curvature of space-time itself. And once you understand these things, once these ideas really sink into your consciousness, the event horizon stops being a mysterious, inexplicable phenomenon and becomes, instead, a natural and inevitable consequence of the universe's fundamental structure. Consider for a moment the profound implications of this. There are places in the universe where the rules change so dramatically that escape becomes impossible. There are points of no return, and these points exist not because of some external barrier or some exotic unknown physics, but because of the curvature of space-time itself, because of the bending and warping of reality that occurs in the presence of extreme mass and density. It's a humbling realization. It suggests that the universe is far stranger, far more extreme, and far more profound than our everyday experience might lead us to believe. It suggests that reality itself has depths and complexities that we're only beginning to understand, and it invites us to continue exploring, to keep asking questions, to maintain our sense of wonder about the cosmos and our place within it. The mechanism by which light becomes trapped at the event horizon is related to something called the redshift effect near black holes. As light travels through curved space-time as it fights against the intense gravity near a black hole, its wavelength increases, its frequency decreases, and its energy diminishes. This process is called gravitational redshift, and it's a direct consequence of general relativity. For light trying to escape from near the event horizon, this redshift becomes more and more pronounced the closer it gets to the black hole. From the perspective of a distant observer, watching the light try to escape, the light appears to move more slowly, its color appears to shift toward the red end of the spectrum, and its brightness appears to diminish. Eventually, when the light reaches the event horizon itself, it appears to come to a complete stop, with an infinite redshift. Its wavelength becomes infinite, its frequency becomes zero, and it effectively disappears from view. But what's truly remarkable is that this isn't an optical illusion or a trick of perspective, it's a real physical effect. The light genuinely is being slowed down by the gravity of the black hole. Time itself is moving slower near the event horizon compared to distant regions of space. A clock placed near the event horizon would tick more slowly than a clock far away. This time, dilation is a direct prediction of general relativity, and it's been measured and confirmed through careful experiments. Atomic clocks at different altitudes on Earth tick at slightly different rates due to the Earth's gravity, and this difference is exactly what Einstein's equations predict. The effect is tiny near Earth, but near a black hole, it becomes enormous. At the event horizon, time dilation becomes infinite. Time itself, as experienced by a distant observer, effectively stops. This brings us to a profound realization. The event horizon isn't actually a physical barrier where light crashes into something and bounces back. Instead, it's a boundary where time itself becomes infinitely dilated, where the rate at which time passes becomes infinitely different from distant regions. For light trying to escape, this means that as it climbs out of the gravitational well of the black hole, its journey takes longer and longer, requires more and more time. From the perspective of someone far away, watching this light try to escape, it appears to move slower and slower. Eventually it appears to reach the event horizon and stop completely, its journey taking infinite time to complete. But for the light itself, there's no paradox. Light always moves at the speed of light. The geometry of spacetime simply becomes configured in such a way that paths leading away from the black hole curve back toward it. There is no path through spacetime that leads away from the black hole and out toward distant space. If you're still here with me, still contemplating these deep and profound aspects of black holes and event horizons, I want to acknowledge the remarkable feat of imagination it requires to follow this reasoning. These concepts are genuinely difficult to wrap your mind around. They go against our everyday intuitions about how the world works. They require us to think about space and time in completely new ways, and yet they're based on solid mathematics, confirmed by observations, part of the framework of modern physics that has proven itself over and over again to be correct. So what aspects of this are you finding most mind-bending, most fascinating, most worthy of contemplation? Is it the idea that time itself can dilate and slow down? Is it the notion that light is trapped not by a physical barrier, but by the geometry of space itself? Is it the profound implication that there are truly places in the universe where escape is impossible? Please, share your thoughts in the comments below. Tell me what's resonating with you as we journey deeper into this cosmic mystery. The deeper we go in understanding the event horizon, the more we encounter fundamental questions about the nature of reality. One of the most intriguing aspects involves something called the information paradox, a puzzle that has occupied the attention of theoretical physicists for several decades now. Here's the crux of the problem. According to classical general relativity, anything that falls into a black hole, any information contained in that matter, is forever lost to the outside universe once it crosses the event horizon. The black hole could swallow the entire Library of Alexandria, every book, every piece of information about human civilization, and none of it would ever escape. Once past the event horizon, the information would be trapped, presumably destroyed when it reached the singularity at the black hole's heart. But this seems to violate one of the most fundamental principles of quantum mechanics, the principle that information is never truly destroyed, that the universe retains a record of everything that happens in it. This paradox has inspired some of the most creative thinking in theoretical physics, with physicists proposing various resolutions from holographic principles to the idea that information might be encoded in subtle correlations in the radiation that black holes emit. And this leads us to perhaps the most profound mystery of all, the discovery that black holes aren't completely black. This discovery came from Stephen Hawking in 1974, when he proposed that black holes can actually emit radiation. According to quantum mechanics, the region around a black hole isn't empty vacuum but a seething foam of virtual particles constantly popping in and out of existence. Near the event horizon, Hawking proposed, something remarkable happens. If a pair of virtual particles forms near the event horizon, with one particle inside and one outside, it's possible for the particle outside to escape to infinity as real radiation, while the particle inside is pulled past the event horizon. From the perspective of a distant observer, this looks like the black hole is emitting radiation and losing mass. Over timescales that would be extraordinarily long for large black holes, this process would cause the black hole to gradually evaporate, losing mass and energy until eventually it disappears completely in a final burst of radiation. This discovery revealed that black holes are not eternal, unchanging features of the universe. They're dynamic objects that interact with the quantum vacuum around them. They can lose mass through this Hawking radiation process, and they can eventually evaporate away entirely. It's a stunning realization that adds another layer of complexity to our understanding of black holes and event horizons. It suggests that even these most extreme objects, these cosmic regions of no return, are subject to the laws of quantum mechanics. They're not exceptions to the rules of physics, they're manifestations of those rules in extreme form. The event horizon, rather than being a final, absolute barrier that separates the universe into regions that can never communicate, becomes something more subtle, a boundary within a dynamical system where matter and energy are constantly being exchanged, where quantum effects play a crucial role even in the strongest gravitational fields. The process of Hawking radiation also offers a potential resolution to the information paradox. If information can't escape from within the event horizon directly, perhaps it can escape through the Hawking radiation process itself. Perhaps the information about what fell into the black hole becomes encoded in the radiation that the black hole emits. As the black hole evaporates, all the information that ever fell into it is gradually released back into the universe. This idea remains controversial and unproven, but it represents the kind of creative thinking that physicists engage in when confronted with profound mysteries. It shows how the study of black holes and event horizons pushes us to the very frontiers of our understanding, forcing us to reconcile different branches of physics that we don't yet fully understand. As we continue through this night's exploration, think about what all of this means. The event horizon is the point of no return for light because of the fundamental geometry of spacetime in that region. It's not because of a wall or a force field or anything material, it's because space and time themselves have been warped so profoundly by extreme mass and gravity that the very concept of away from the black hole ceases to exist beyond that boundary. Every direction points inward, every path curves back toward the singularity. Light, constrained to follow the laws of physics just like everything else in the universe, finds itself trapped, unable to escape, unable to reach the distant stars, and yet this isn't a final, absolute barrier. Quantum effects can operate at the event horizon. Information might escape through Hawking radiation. The universe maintains its subtle ways of preserving what seems lost. The event horizon is profound and mysterious, yes, but it's also part of a coherent, unified picture of how the universe works at all scales, from the quantum to the cosmic. And as we move forward into deeper contemplation of what this all means for our understanding of reality and our place within the universe, we carry with us this newfound appreciation for the sophistication and subtlety of the cosmos we inhabit. The realization that black holes exist, that they operate according to principles we can understand and predict, and that they fundamentally teach us about the nature of space and time themselves, brings us to a crucial turning point in our exploration. We've now moved from the realm of initial wonder into the territory of evidence and speculation, where we can examine what we know, what we've observed, and what remains genuinely mysterious. As we journey deeper into this night of cosmic contemplation, I want to invite you to consider not just how the event horizon works, but what its existence tells us about the broader structure of reality. What does the fact that such extreme phenomena exist in our universe reveal about the fundamental laws that govern everything? What can we learn from studying these cosmic laboratories of extreme physics? The evidence for black holes has accumulated gradually, carefully, methodically, building layer upon layer of confirmation that these objects are not just mathematical abstractions, but genuine features of our cosmos. One of the most compelling lines of evidence comes from our observations of X-ray binaries. systems where a black hole orbits in close proximity with a normal star. In these systems, the black hole's powerful gravity tears material away from its companion star, pulling streams of gas and dust across the space between them. This material doesn't fall straight into the black hole. Instead, it spirals inward, forming an accretion disk, a swirling maelstrom of falling material. As the material in this disk accelerates, as friction heats it to temperatures of millions of degrees, it emits intense X-ray radiation. Some of the most famous X-ray binaries include Cygnus X1, discovered in the 1960s, and GRS 1915 plus Monroe 5, discovered in 1992. Observations of these systems have provided some of the most direct evidence that black holes exist. The way we identify black holes in these systems is quite elegant, really. We measure the orbital properties of the visible star, its brightness, its position, how it moves in space. From these measurements, we can determine the mass of its unseen companion. And here's the crucial part. If we calculate that the mass of the companion object exceeds the maximum mass that a neutron star can have, and neutron stars are the densest objects we know of besides black holes themselves, then the only explanation is that the companion must be a black hole. We've identified dozens of stellar mass black holes this way. Each one is a confirmation that the universe really does contain objects that can trap light itself. Each one adds to our confidence in our understanding of how gravity works in these extreme regimes. But stellar mass black holes are only part of the story. The most recent and most dramatic evidence for black holes has come from the direct detection of gravitational waves. In 2015, scientists working with the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected the gravitational waves from the merger of two black holes, each about 30 times the mass of our Sun. These gravitational waves are ripples in spacetime itself, caused by the motion of the massive black holes as they spiraled inward toward each other. The detection confirmed not only that black holes exist, but also that gravitational waves exist exactly as Einstein predicted. It was a moment of profound scientific achievement, a confirmation of predictions made a century earlier, a direct observation of space and time itself being warped and rippled by the motion of massive objects. And it opened an entirely new window on the universe. We could now observe the universe not just through light, visible light, X-rays, radio waves, but through the subtle vibrations of space-time itself. Since that first detection, LIGO and other gravitational wave observatories have detected dozens more black hole mergers, each one confirming our understanding of these objects, each one revealing new details about how black holes behave. These observations have also revealed something unexpected. Some of the black holes being detected are more massive than we expected stellar black holes to be. According to our understanding of how stars form and evolve, there should be a limit to how massive a black hole can become through the collapse of a single star. But some of the black holes being detected seem to exceed this limit. This has sparked new questions, new investigations into how such massive black holes could form. Perhaps they form through the merging of smaller black holes. Perhaps there are exotic formation mechanisms we haven't yet considered. The universe continues to surprise us, to reveal new layers of complexity and richness that we didn't anticipate. And then there's the supermassive black holes at the centers of galaxies. These are black holes with masses millions or billions of times that of our Sun. They're found at the heart of essentially every large galaxy astronomers have studied, including our own Milky Way. The existence of these supermassive black holes was inferred long before we had direct evidence of them, simply from the orbital motions of stars and gas clouds in galactic centers. Stars were observed moving with velocities that could only be explained if they were orbiting an invisible, incredibly massive object. By measuring these orbital velocities and applying the laws of physics, astronomers could calculate that the central object must have a mass of millions of solar masses. The only object that could have such an enormous mass compressed into such a small space is a black hole. So astronomers concluded with high confidence that supermassive black holes must exist at galactic centers. The breakthrough came in 2019, when the Event Horizon Telescope collaboration released the first image of the event horizon of a black hole. The image showed the supermassive black hole in the galaxy M87, a giant elliptical galaxy about 55 million light-years from Earth. What the image revealed was a dark central region, the shadow of the event horizon itself, surrounded by a bright ring of light from material being infallen into the black hole. The image confirmed with unprecedented clarity that the event horizons of black holes are real, that they have the size and shape that Einstein's equations predict, that they truly represent boundaries where the geometry of space-time has been twisted to its most extreme. It was one of the most remarkable astronomical achievements in modern history, a direct observation of one of the most extreme objects in the universe, a vindication of a century of theoretical work. If you're still with me at this point in our journey, if you followed along through all these intricate details and complex ideas, I want to acknowledge your dedication to understanding these cosmic mysteries. What we've been exploring together isn't easy. It requires holding multiple complex ideas in mind simultaneously. It requires accepting that the universe is far stranger and more profound than our everyday experience suggests. It requires us to be comfortable with uncertainty, with the boundaries of our current knowledge, with the profound mysteries that remain unsolved. So I want to ask you directly, what have you found most interesting in everything we've explored so far? What aspect of the event horizon, what piece of the puzzle of black holes and gravity and space-time has captured your imagination most powerfully? Please share your thoughts in the comments. Tell me what's resonating most deeply with you as we journey through this cosmic mystery together. Your thoughts and reflections help us understand what aspects of the universe truly matter to people, what questions are worth asking, what mysteries are worth exploring. The evidence for black holes comes from many different directions, many different observational approaches, all converging on the same conclusion: black holes are real. But evidence, while important, is only part of the story. We also need to engage with the deeper implications of what black holes tell us. What does the existence of event horizons mean for our understanding of physics? What does it suggest about the ultimate nature of reality? These are philosophical questions as much as scientific ones, and they require us to think carefully about what we know and what we're still trying to understand. One of the most profound implications of black holes is that they demonstrate the limits of classical physics. In the classical Newtonian view of gravity, there's nothing special about the escape velocity reaching the speed of light. In that view, gravity is just a force, following the inverse square law, predictable and well-behaved. Objects can escape from any gravitational field if they have enough velocity. But in the relativistic view, the view provided by Einstein's general relativity, the speed of light is a fundamental barrier, not just a practical limit. Nothing can exceed the speed of light. Nothing. And if escape velocity exceeds the speed of light, then escape truly becomes impossible. This represents a qualitative change in the nature of physics, a change in how reality itself is structured at its deepest levels. Moreover, black holes force us to confront the breakdown of our classical understanding of space and time. In the Newtonian view, space is three-dimensional Euclidean space, the kind of space we're familiar with from everyday life. Time is separate from space, flowing uniformly forward for all observers. But Einstein showed us that space and time are intertwined, that they form a unified four-dimensional structure called space-time, that this structure can be curved and warped by the presence of mass and energy. Black holes represent the extreme case of this principle. They're regions where space-time is curved so profoundly that our classical intuitions break down completely. The concepts of simultaneity, of cause and effect, of the passage of time, all of these become ambiguous or problematic near a black hole. We need quantum mechanics, string theory, or some new framework that we haven't yet discovered to fully understand what's happening in the most extreme regions near the singularity. This brings us to one of the most important lines of speculation in theoretical physics: what happens at the singularity? According to general relativity, all the mass of a black hole is concentrated at a singularity, a point of infinite density at the center of the black hole hidden behind the event horizon. But infinite density is nonsensical. It's a sign that our theory has broken down, that it can't describe what's actually happening. Physicists believe that at the singularity, quantum effects must become important. The quantum nature of space-time itself must play a role. There might be a quantum structure to space-time at extremely small scales, scales far smaller than any human technology could ever probe directly. Understanding the singularity requires a theory of quantum gravity, a unified framework that combines general relativity with quantum mechanics. Such a theory remains one of the great unsolved problems in physics. String theory, one of the leading candidate theories of quantum gravity, suggests that at the smallest scales, space and time might have additional dimensions beyond the three spatial dimensions and one temporal dimension that we experience. These extra dimensions might be curled up or compactified, so small that we can't directly perceive them. String theory also suggests that at the Planck scale, a scale of about 10 to the minus 35 meters, far smaller than any atomic nucleus, spacetime itself might have a granular or discrete structure, rather than being smooth and continuous. Some theorists suggest that this quantum structure of spacetime might modify what happens inside black holes, that it might prevent true singularities from forming, replacing them instead with some kind of quantum structure that we don't yet fully understand. Another intriguing possibility comes from the holographic principle, a deep idea in theoretical physics that suggests that the physics of a region of space can be described entirely by information encoded on its boundary. Applied to black holes, this principle suggests that the information about everything inside a black hole might be encoded on its event horizon. Rather than being lost forever when something crosses the event horizon, the information would be available on the boundary itself. This idea, while still speculative, represents the kind of creative thinking that physicists engage in when confronted with profound mysteries. It shows how exploring black holes and event horizons pushes us to rethink our most fundamental assumptions about how the universe works. The question of what happens to information that falls into a black hole remains one of the deepest unsolved puzzles in physics. It's more than just an abstract theoretical question. It touches on fundamental issues about the nature of information, the nature of quantum mechanics, the nature of reality itself, and it shows us that our current understanding of physics, while remarkably successful in many domains, has clear limits and boundaries where new physics must emerge. Black holes are laboratories where we can test these boundaries, where we can push our understanding to its limits and see what breaks, where we need new ideas and new frameworks. As we contemplate the evidence for black holes and the questions they raise, we're really engaging in one of the most fundamental human activities, the attempt to understand the universe, to see through the fog of our ignorance, to glimpse the underlying order and structure of reality. Black holes challenge us to expand our minds, to accept ideas that contradict our everyday intuitions, to live comfortably with mysteries and unanswered questions. And in doing so, they teach us something valuable not just about physics, but about the human condition, about our capacity for wonder, our drive to understand, our ability to grasp truths that seem impossible. The journey from the initial discovery of black holes as theoretical constructs in Einstein's equations to the current era of direct observation and detection represents one of the great success stories of human science. It's a story of persistence, creativity, and the gradual accumulation of evidence and understanding. It's a story that continues to unfold even now, with new observations, new questions, new mysteries emerging. And the event horizon, that boundary where light itself is trapped, remains at the heart of this story, a symbol of the limits of escape, the power of gravity, and the profound strangeness and beauty of our universe. Consider this. The event horizon isn't just a curiosity or a technical feature of black holes, it represents something deeply important about how the universe is structured. It demonstrates that there are genuine limits in nature, not just practical limits, but fundamental, absolute boundaries where the rules change. It shows us that reality can be far more extreme, far more alien than our everyday experience suggests, and it invites us to continue asking questions, to keep exploring, to maintain our sense of wonder about the cosmos and the deep principles that govern it. The process by which we've come to understand event horizons, the way scientific knowledge accumulates and evolves, is itself a fascinating story. It involves not just brilliant theoretical physicists making mathematical discoveries, but also patient observers using increasingly sophisticated instruments to observe the universe and test predictions. It involves international collaboration, the combination of efforts from many countries and institutions, all working toward the common goal of understanding how the universe works. It involves failed hypotheses being abandoned and new ideas being developed. It involves the humbling realization that nature is far more subtle and complex than we initially suspected. And this brings us to a crucial realization. Our current understanding of black holes and event horizons, while far more sophisticated and nuanced than what we knew even a decade ago, is still incomplete. There are still profound mysteries to be solved. There are still questions about the nature of singularities, about what happens inside black holes, about the ultimate fate of black holes and the information they contain. These mysteries represent opportunities for future discoveries, for new insights into the fundamental nature of reality. They remind us that science is not a closed body of knowledge, but an ongoing process of discovery and understanding, a continuous dialogue between theory and observation, between our ideas about how the universe works and what we actually observe when we look at the universe. The study of event horizons has also revealed something profound about the nature of physics itself. It's shown us that physics is not merely a collection of disconnected facts and rules, but rather a coherent, unified framework where different principles are deeply interconnected. General relativity, which describes gravity on large scales, must somehow be compatible with quantum mechanics, which describes the behavior of matter and energy at small scales. Black holes are places where both general relativity and quantum mechanics are important, where they cannot be ignored. This forces us to develop new theories that unite these two pillars of modern physics. It's a challenge that has occupied theoretical physicists for decades, and while we don't yet have a complete answer, the attempt to find their answer has led to many deep insights and creative ideas. The event horizon, in this context, becomes more than just a boundary where light is trapped. It becomes a window into the deepest questions about the nature of reality. It becomes a testing ground for our ideas about quantum gravity, about the ultimate structure of spacetime, about what happens at the limits of physics. And in exploring these questions, we're not just advancing scientific knowledge, we're participating in one of humanity's most fundamental and noble endeavors, the quest to understand the universe and our place within it. Each observation of a black hole, each new gravitational wave detection, each theoretical advance brings us a little closer to that understanding. And the journey itself, the process of asking questions and seeking answers, is itself deeply worthwhile. If you've been following along with us through this exploration, through all these detailed discussions of evidence and speculation, quantum mechanics and general relativity, the formation of black holes and the nature of event horizons, then you've been engaging in exactly this process. You've been stretching your mind to encompass ideas that challenge your everyday intuitions. You've been building a mental model of how the universe works at its most extreme. You've been participating in humanity's collective effort to understand the cosmos, and that's something genuinely remarkable. So I want to ask you once more, what have you found interesting in all of this? What questions are still burning in your mind? What aspects of black holes and event horizons are you finding yourself returning to, thinking about, unable to let go of? Please share your reflections in the comments. Tell me what's capturing your imagination as we journey deeper into these cosmic mysteries. Your thoughts help us understand what truly matters, what questions are worth pursuing, what mysteries are worthy of our contemplation and our wonder. End.